The video tonight that I am creating for you is to guide you through some of these mole practice problems. But before we get started, I wanted to just kind of let you know about a couple of things. Um, First of all, when we're dealing with moles, we're dealing with the SI unit for the amount of substance, and we talked about that. Um, just as importantly, though, is because it's the amount of a substance, it can have a lot of different meanings. So they can be used as a variety of conversion factors. So there are three main ways that I can come up with that the mole can be used as a conversion factor. The first way it can be used as a conversion factor is to say that 1 mole of substance, whatever that substance might be, is equal to 6.022 times 10 to the 23rd particles of that substance. Okay, again, whatever that substance might be. Remember, in chemistry, the particles generally are atoms, molecules, ions, or formula units. Okay. The second way by which we can use moles for a conversion factor is to know that 1 mole of substance, whatever that substance might be again, is equal to some number x grams of substance. Okay. This is referred to as the molar mass, or the mass of 1 mole. Okay. The third way it can be used, and we probably won't refer to it until we get into the gases and gas laws, is to know that 1 mole of a gas substance, and the condition's got to be at what's called STP, or standard temperature and pressure. 1 mole of a gas substance at STP is equal to 22.4 liters of gas volume. Okay, we're going to focus our attention this evening on the video that I'm creating tonight on these two conversion factors right here. And if we have a good understanding of what's going on with these two conversion factors, then when it comes time for us to talk about 22.4 liters of gas equaling 1 mole of gas, it'll be pretty straightforward for us. Okay, so first things first, let's go ahead and take a look at question number 4. What is the mass of 0.28 moles of iron? All right. Well, in this case, we can see that we're converting directly between mass of iron and moles of iron. So we're going to use that molar mass component. And what we know about the molar mass of iron is that the molar mass is equal to 55.85 grams per mole. Okay, for every 1 mole of iron, it's 55.85 grams. And you can look that up on your periodic table. So from a dimensional analysis standpoint, we can say that there are 0.28 moles of iron. We're going to put that over 1. And what we know is that for every 1 mole of iron right here, there's 55.85 grams. So we want to cancel moles of iron. So 1 mole of iron will go in our denominator, and that's for every 55.85 grams of iron, which will go into our numerator. Okay, your moles of iron will cancel, and what we're left with is 0.28 times 55.85. So if we go over to our calculator, we can type that in, 0.28 times 55.85. We can see that it's equal to 15.638. So if we come back into here, we can see that this is equal to 15.638 grams of iron divided by 1 times 1, or 1. And because we're only using two significant figures, we want to make sure that we are going to round this to two significant figures, which would equal 16 grams of iron. Okay, when we multiply and divide, we always use the smallest number of significant figures for our answer. So that's pretty straightforward. Okay, pretty basic. When we're going from grams to moles, we're going to use the molar mass, or if we're going from moles to grams, in this case, we're going to use molar mass, and we're going to cancel our units. Okay. The next example, how many moles are in 1.0 times 10 to the 9th atoms? Well, you might be asking yourself, well, atoms of what? The interesting thing about the mole is that it doesn't matter. If we're talking about atoms of an element, we know 1 mole of any substance, okay, 1 mole of any element is going to equal 6.022 times 10 to the 23rd particles, or in this case, atoms. So if we know that we've got 1.0 times 10 to the 9th atoms of something, whatever that something might be, and we know that for every 1 mole, there are 6.022 times 10 to the 23rd atoms. We can set it up so that atoms cancel. 6.022 times 10 to the 23rd atoms for every 1 mole of whatever substance that might be. Now your atoms are going to cancel. What you're left with is the unit for moles, so that's going to be equal to 1.0 times 10 to the 9th moles divided by 6.022 times 10 to the 23rd. So again, we go over to our calculator. Now this is interesting because we can put numbers in scientific notation in for the first time. A couple of things to keep in mind when we're doing that. First of all, we want to make sure we use parentheses around anything that has scientific notation on it. So we're going to take 1.0 times 10 to the 9th and divide it by 6.022 times 10 to the 23rd. So we'll open the parentheses and type in 1.0 times 10 to the 9th. Well, we can use the scientific notation function on here, and it's a little, I don't know how well you can see that. I'll try to zoom in a little bit. No, it's not letting me zoom in. We can actually look at above the comma button is this EE. If we select EE, that puts a little e up here. That means times 10 raised to some power. So when we say 1.0 E9, and then close parentheses, that means 1.0 times 10 to the 9th. Okay? So that takes care of your numerator. And we want to divide that by 6.022 times 10 to the 23rd. So we open our parentheses again. 6.022. Again, we want to say times 10 to the 23rd, so we can go second E. That E is above the comma. 23. Close your parentheses. And hit enter. And what we're left with as a value is 1.66. And we can see that this is times 10 to the negative 15th. Okay? So when we go ahead back over here, we can see that it's going to be 1.66 times 10 to the negative 15th. Now again, two significant figures are what we started with. We want 2 in the end, so the 1.66 will round to 1.7 times 10 to the negative 15th, and the unit is moles of, again, whatever substance that might be in this particular case. Okay? Okay, this next example is what's going to marry those two together. This is question 14. And so we're being asked now, how many molecules are 52 grams of CO? So in your minds, what you should be thinking about is that we need to somehow connect grams to molecules. So the only way to connect grams to molecules is if we take grams of CO and connect it to moles of CO. And then if we take moles of CO, we can then connect it to molecules of CO. See, the thing is, grams of CO does not connect with molecules of CO. If we go back to the initial set of conversion factors that we talked about, we can see 1 mole of substance is equal to some number of particles, molecules in this case, and 1 mole of substance is equal to some number of grams of substance. So really, there's no direct connection. I mean, yeah, the 1 mole is what they have in common, but the thing to keep in mind is that when we're talking about them having 1 mole in common, we want to make sure that we are using that as our connection. So what that means is that we can go ahead and we can convert this from grams of CO to moles of CO, and then from moles of CO to molecules of CO. So we need to first know what's the molar mass of CO. Well, the molar mass of CO is made of 1 carbon and 1 oxygen, so that's really easy because what we end up with is 12.01 plus 16.00, which is equal to 28.01 grams per mole. Okay, so that's the molar mass of carbon monoxide. So now we can say, okay, we got 52 grams of CO. We can put that over 1. And we can say for every 28.01 grams of CO, we know that's going to be 1 mole of CO. If we stopped here, we'll cancel our grams. What we'll be left with is moles of CO. Okay, and that's all fine and well. But we're trying to get to molecules. So if we can go from grams to moles, we can then take moles and convert it into molecules by saying, all right, well, we know that every 1 mole of CO is going to be equal to the same number of 6.022 times 10 to the 23rd molecules of CO. Your moles of CO now cancel. What you're left with are molecules of CO. Okay, so now it's arithmetic. So it's 52 times 1 times 6.022 times 10 to the 23rd. That works out to be your numerator. So if we do that, we end up with 52 times, again, we've got this number in scientific notation, so we'll open our parentheses, 6.022. We want to put it in times 10 to the 23rd, so we second E 23, close the parentheses. That takes care of our numerator, it would be times 1. We end up with 3.13 times 10 to the 25th. So if we come back over here, we can see that the numerator works out to be 3.13 times 10 to the 25th, and the unit is molecules of CO. That whole thing is going to be divided by 28.01 times 1 times 1, or 28.01. So now if we come back into our calculator, we can say, okay, well this whole thing, this 3.13 times 10 to the negative 25th, will be divided by 28.01, enter, and we end up with 1.11797 times 10 to the 24th. So rather than writing a number down and modifying it, we can see there's two significant figures here. This is a lot more than two significant figures here, but we can go ahead and come up with a better answer for that by saying that it's equal to 1.1 times 10 to the 24th molecules of CO. Now we can evaluate this answer pretty easily because we know that the molar mass is going to be 28.01 grams per mole. Okay, we can see that the mass we're starting with is 52, which isn't quite which isn't quite double the 28.01. Okay, it's not quite double, but it's close. So double 1 mole of molecules would be 1.2 times 10 to the 24th. Well, it's not quite double, so our answer of number of moles shouldn't be quite double either, and we're ending up with 1.1 times 10 to the 24th. I hope what I just said there is making some sense to you. Okay. Another example very similar to the previous one. What is the mass of 3.01 times 10 to the 23rd formula units of Fe2O3? Okay, well, the first thing we need to do is we need to understand that we're going from some number of formula units to mass. Okay, so we're going from formula units of Fe2O3 to mass, but in order to do that, we need to first go to moles of Fe2O3, because we know that for every 1 mole, there's 6.022 times 10 to the 23rd formula units. And then once we have those moles, we can go to grams of Fe2O3 using the molar mass. Okay, so we know that we're going to need the molar mass of Fe2O3. Don't know it off the top of my head, but we do know that the mass of iron is 55.85 and the mass of oxygen is equal to 16. So we can say, all right, in our parentheses, we're going to say 2 times 55.85, which is the mass of iron, and we want to add that to 3 times the mass of oxygen, which is 16, and we're going to close those parentheses and enter, and we end up with 159.70. Okay, so we know that the molar mass equals 159.70 grams per mole for Fe2O3. Now that we've got that information, we can say, all right, we've got 3.01 times 10 to the 23rd formula units of Fe2O3. We want to go ahead and convert that into grams. So what we need to do is we need to say, all right, for every 6.022 times 10 to the 23rd formula units, there's going to be 1 mole of Fe2O3. And to be honest, we need to make sure we say formula units of Fe2O3 just so that we've got the same language going on here. These cancel out. All right, what we're left with is moles of Fe2O3, and we know that we want to get rid of by turning it into grams. For every 1 mole of Fe2O3, you're left with 159.70 grams of Fe2O3 as we calculated. So now we're going to go ahead and just clean up our arithmetic. All right, we're going to do 3.01 times 10 to the 23rd. So again, open parentheses, 3.01 times 10 to the 23rd, second E, 23. We'll close those parentheses because that scientific notation is all set. And we're going to say times 159.70, enter. And the total for our numerator is 4.80, 4.81 times 10 to the 25th. So 4.81 times 10 to the 25th grams of Fe2O3, but it should make sense that that's way too high. We haven't divided it by Avogadro's number yet, so it's going to be divided by 6.022 times 10 to the 23rd. Come back over here. We're going to say, okay, take this answer, divide it by, open parentheses, 6.022 times 10 to the 23rd, close parentheses, enter. And what we're left with is 79.82 grams. Okay, again, 3 significant figures is what we want, so we want 3 in the end, so it'd be 79.8 grams. Equals 79.8 grams Fe2O3. Now again, that should make sense as well. This 3.01 times 10 to the 23rd is almost exactly half of Avogadro's number, so that literally means we have half a mole, which means we should have about half the molar mass, and that's about what we have going on with this relationship right here. All right, one last one to talk about today. I know this has been a lot. We're going to take 1.2 times 10 to the 23rd atoms of Cl and convert it to moles of CuCl2. So we got a lot going on right here. Okay. The nice thing about this is we don't need to be dealing with masses. What we do know is that we have 1.2 times 10 to the 23rd atoms of Cl. Okay, we'll put that over 1. Now, the thing about it is that we know that when we look at this formula, there are 2 atoms of Cl for every 1 formula unit. Okay, 2 atoms of Cl for every 1 formula unit of CuCl2. So we want to make sure we take care of that. There's 2 atoms of Cl for every 1 formula unit of CuCl2. Okay? Well, now we want to take those formula units and convert them into moles. How? Because we know that for every 6.022 times 10 to the 23rd formula units of CuCl2, we're going to end up with how many moles of copper 2 chloride? 1 mole of CuCl2. Atoms of chlorine will cancel, formula units will cancel, and what we're left with is 1.2 times 10 to the 23rd times 1 times 1, so that's going to be equal to 1.2 times 10 to the 23rd, and the unit will be moles of CuCl2. That's all going to be divided by 6.022 times 10 to the 23rd times 2, which is about 1.2044 times 10 to the 24th. 24th, okay, a little hard to see. So we come back into our calculator over here. Open a parentheses first. 1.2 times 10 to the 23rd, close parentheses. We want to divide that by 1.2 times 10 to the 24th, close parentheses, and we should be able to see what's going to go on right there if we have some understanding of arithmetic. We end up with 0.1, but we want 2 significant figures because that's what we start with, 0.10 moles of CuCl2. Okay? The reality is that these practice problems are a lot. There are many, many ways to be dealing with moles, and I tried to give you a snapshot of how we go about these here. Hopefully there's enough to guide you through it so you can gain an appreciation for what's going on. It's my hope that you're able to work your way through some more of these questions. Please feel free to email me if you have further questions. If you need help running the calculators or something like that, let me know, and then we'll go from there. But in the meantime, good luck working on these practice problems, and we'll see you next time.